Let's continue in section 4.3. Let's learn how to solve some basic logarithmic equations. Before we see the first example, I want to start with a statement I made in the previous video. I wrote the log base 2 of 2 to the y is equal to y. And that was really the whole point of defining a logarithm, was to say that it would be the opposite of the base, the log base 2 would be the opposite of the base 2 exponential. So the logarithm is defined as the inverse or the opposite, so it must cancel. So we can think of starting this expression with a y and applying a base 2 exponential to it to get 2 to the y, and then doing the opposite of that. Log base 2 of that whole thing means that those two must cancel, and we get right back to y. And so let's generalize just a little bit. We don't have to use base 2. We could use base a, for instance, and the variable could be y, or it could be x, or it could be some other letter. But the point is that the log base a of a to the x is equal to x by the very definition of a logarithm as the inverse operation. And then we can extend that idea just a little bit. We can write, let's see here, 2 to the log base 2. Instead of using y or x, let's use another letter. Let's use t, for instance. The idea is the same. What we have now is we're starting with t, and we're doing two things. First, we apply the log base 2 to that t, and then we apply the base 2 exponential to that. So there are two operations on the t. There's the log base 2, and then there's the base 2 exponential. And of course, those are opposite operations, so they cancel each other out. So what are we left with? I bet you said t. And so we can generalize that just a little bit. We can say base a raised to the log base a of x is equal to x. So these two statements together have a fancy name. They're called the theorem on inverses. And really all we're saying is that the logarithm is the inverse of the exponential, and the exponential is the inverse of the logarithm. So if we want to solve a logarithmic equation, there are actually two ways that we're going to do this, but let's start with an idea from this theorem on inverses. Let's use the opposite operation to make an exponential. Let's use the opposite operation to make an exponential. And then just cancel and then just cancel the opposite operations. Okay, so let's give it a go. So here in example 4a, we have an equation that says log base x of 8 over 27 is equal to 3. And so let's do the opposite operation. If we have a log base x, then the opposite operation is a base x exponential. And so we'll put the base x underneath log base x of 8 over 27. And so the log base x of 8 over 27 goes up into the location of the exponent, and then the base underneath it is an x, is this brand new x here. And then we just have to do the same thing on the other side, and we get x to the third. And then the beautiful thing is that the base x exponential and the log base x cancel, and we're just left with 8 over 27 is equal to x cubed. We could switch the two sides and say x cubed is equal to 8 over 27. We could take the cube root of both sides, and the cube root and the cube cancel, and we're just left with x is equal to, the cube root of a fraction is just the cube root of the numerator over the cube root of the denominator. So our answer is 2/3. And there we go. I want to make one more observation here. Look at the original problem, the logarithm, and then look at this step here. We could have skipped the base x underneath both sides. How could we do that? Well, couldn't we just rewrite the logarithm as an exponential? If we rewrite the logarithm as an exponential, the base is x, so base x in the exponential. 3 is the exponent on that base. X to the third makes the argument 8 over 27. So there's a little shortcut if you like. I think it's real important that you know both ways. So let's practice both ways. Here in part B, let's take the shortcut and then we'll show the opposite operation as well. If you want to take the shortcut, then you're going to rewrite the log as an exponential. What's the base? 4. What's the exponent? It's the number on the other side. It's the 5/2, and that equals the argument. And we've solved for x in one step. If we'd like to, we can go on from there and simplify it and get our final answer. But before we do that, let's back up. Let's apply the opposite operation to justify this step. So if we back up just a little bit, then we could put a base 4 underneath both sides of the equation. And then on the left side, the base 4 exponential and the log base 4 cancel, and we're just left with x is equal to 4 to the 5/2. I guess it would be nice to get x over here on the left side anyway, so we'll write 4 to the 5/2. You could put this in your calculator, but it'd also be fun just to simplify it. We talked about how to do this in a previous section. We can deal with the numerator and denominator separately. We can split them apart using a property of exponents. And then 4 to the 1/2 is just the square root of 4. And so the square root of 4 is 2 raised to the 5th gives us 32. And there's our answer. Okay, let's do one more. So here, let's apply the base 49 on both sides. If you want to skip that step, that's okay. But be sure to understand it. Also, I'll warn you that we're going to see more complicated equations involving exponentials and logarithms in section 4.5. So we're laying a foundation for harder problems to come in section 4.5. Okay, so we have a log base 49. So we're going to put a base 49 underneath each side of the equation. And then the 49 and the log base 49 cancel. And we've got the cube root of 7 is equal to 49 to the x. And actually, wow, do you remember how we solved this in section 4.2? What we did is we found a common base. So the cube root of 7 is the same as 7 to the 1/3 power. And 49 is the same as 7 to the 2nd power. So 7 to the 1/3 is equal to 7 raised to the 2x. With the bases the same, we can just drop them away. And then we'll have 1/3 is equal to 2x. Or if we multiply both sides by a half, we'll get our answer, x equals 1/6. And we're done.